Let me introduce you to a game theory problem called El Farol. We have 50 people in a town. We also have a bar named El Farol. So the whole concept is incredibly simple. Every townsperson wants to visit El Farol once per week. Going to the bar is not free. As you can see, it incurs a cost of 1 point. Well, also, you get the reward of 2 points once you get to the bar, since you get to have some fun. Well, unless the bar is crowded, means it has more than 30 people visiting at once. In that case, you get a reward of half point. Or you could stay home and enjoy the stars, you get a reward of 0, but don't pay any price of going to the bar. Let's sum it all up. So you could stay at home, you get 0 points for the reward. You can go to the bar and it's crowded, then you get 0.5 points, minus 1 cost, negative 0.5 for the reward. Or you can go to a bar and it's not crowded, then you get 2 points for the reward, minus 1 cost, plus 1 points for your reward. And now let's put them all to the right so we can reference them later. Well, townspeople are not allowed to communicate, but we do know about the history of attendance, which turns this game into a quite complex situation. And we'll be able to explore some fascinating social dynamics which can emerge here, because different types of people can employ different strategies. In real life, people will become trend followers, contrarians, Pavlovians, and so on. But we will simulate these real-life strategies in my second video on Farol. In this video, I'm going to focus on finding an optimal symmetric strategy, meaning that the same one is going to be used by every person. In such a strategy, no individual person could change his strategy to a better one, which is known as reaching Nash Equilibrium. And that's what we're gonna be looking for. So let's start simple. Can everyone just always go to the bar? Well, that's just trouble, since the bar will always be overcrowded, and everyone gets negative 0.5 points reward. And then any single person would be better off of not going to the bar, which means it is not a Nash equilibrium strategy. How about a more complex one? Should we stay at home at first, or if the bar was overcrowded yesterday, and go to the bar if the bar was not crowded yesterday? Well, the first week no one will go to the bar, while the next one everyone will go, and the bar will be crowded. The next, the bar will be empty again, and so on. Everybody loses, although average reward is now a bit better at negative 0.25. You can also probably see it's again not a Nash equilibrium strategy, since any person can just apply an opposite strategy and be better off. Well, you can try more examples, but in the end, single optimal symmetric strategy just does not exist here. Nash equilibrium is not reachable. But what we can do instead is to randomize every week whether we're going to the bar or staying home. This is also known as a mixed strategy. Well, and there is a symmetric Nash equilibrium mixed strategy for this game. What would you say? At what rate should we go to the bar? Well, for example, in rock, paper, scissors, which similarly does not have a single strategy Nash equilibrium, the intuitive mixed strategy answer is to play randomly 33% each. And intuitive answer is the correct one. So what about overall? What's the intuitive answer? Well, I can tell you mine, since there's 50 people in total, 30 is crowding threshold, that's 60%, right? In that case, I would presume it's also 60%. You know what? Let's simulate it. So we will set the p to 0.6, which is 60%, and I'll also put some epoch averages to the left so you can keep track of what's going on. So we run the simulation. It runs fun so far, but we're gonna speed it up quite a bit and also skip a bunch of weeks since I wanted to run it for 100 weeks in total. And in the end, we're gonna see some results. So, well, you can see average attendance is about 30 people per week, which is very much expected, right? And we got average reward of 0.21, which is great since that's more than zero, it's positive at least. But is it like the best reward? Well, not for everyone, since look at the crowded weeks. We have 40 of them. That's quite a big number. I was wondering if we could maybe start decreasing the p-value and see if we can get rid of these crowded weeks. Let's see how this goes, actually. So now we will run multiple epochs, which is 100 weeks each, and we will keep decreasing the probability, p-value, and we'll see how the reward changes and all the other parameters as well. So you can see right away the reward increases while we get less crowded weeks, And this keeps going on, and while we decrease the p-value, and at this point, maybe you can see, oh yeah, that's pretty much the maximum value, which is at 48% probability of going to the bar. So everybody wins. But is it Nash equilibrium? Well, no, since I'll remind you, Nash equilibrium means that no player can gain advantage by changing his strategy. To demonstrate this, we'll switch to a different chart where you can see individual players' probabilities and rewards. Right now, probabilities are all equal. We set it at 48%, and we'll start decreasing B2's probability, P, just by little, and see what happens with its reward. Well, as you can see, the reward is getting smaller while everyone's staying a bit pretty much the same. They're probably also a bit increasing, but that's not visible really here. Let's reset this and try increasing the probability of B2 of going to the bar. Well, look, it appears that B2 can easily exploit the system by going to a bar all the time, which means that 48% strategy is exploitable and thus is not Nash equilibrium. And you might already see the pattern. If the average reward is positive, any individual can exploit the system by going to the bar more often. So let's increase everyone's probability of going to a bar to the point that the reward is zero for everyone. We need to make players indifferent between going to the bar and staying home. Let's run the simulation and you can guess what the probability of going to a bar will be once the reward reaches zero. The reward is going down, and it seems we're gonna break 60%, which we had initially. And look, at this moment, it seems, yes, it's zero at around 63% mark. At this moment, we did reach Nash equilibrium, since all the rewards are zero. Bar in Nash equilibrium is not useful to townspeople, since they are indifferent to the existence of a bar. There could be a bar, there could be no bar, there could be a Schrodinger's bar. It would make no difference. Let's quickly test this. So let's set P to 63%, and let's start by decreasing the B2's probability of going to the bar. Well, everyone's around 0%, zero reward, so nothing really changes, and Nash equilibrium certainly holds. So let's reset this to 63%, and instead let's start increasing B2's probability of going to a bar. Again, nothing really happens. Well, I don't have enough accuracy to really say, but yeah, everyone seems to stay at around zero reward. So that's the Nash equilibrium at 63%. Now, I don't know about you, but it really wasn't intuitive to me in the beginning. And I still have to twist my mind a bit to really understand that we have to make everyone indifferent to the existence of a bar itself. Well, you know what? Let's try proving this with math. So we'll define RG, reward of going to the bar, to be equal to RH, reward of staying home. RG is, of course, a half point of probability that the bar will be overcrowded. And when we add 2 points that the bar is not crowded, which is 1 minus PO, and when we just take away 1 point for the cost of going to the bar, and RH, we already know it, that's 0. So how do we calculate PO? Well, that's a well-known binomial distribution formula, which really means asking multiple independent yes or no questions, where P is the probability of any individual answering yes, and exactly what we've been calculating so far, the probability of going to the bar. N is of course a number of individuals, which in our case is 49, not 50, since we're calculating this from the perspective of a remaining one, where 49 have already been decided. Let's replace it for 4 and the 49. And k is a number of yeses we're expecting. So of course there's multiple k's, and there's a probability of 30 and 31 and 32. So let's just sum it all up, and we can write it like this. And that's it. That's our probability of a crowded bar. Now we substitute P0 and merge these two formulas into this monster one, and all we need to do now is solve for P, which I'm not gonna do myself. I'm gonna go to Wolfram Alpha now. So there's gonna be the same formula, which I just wrote, just in a bit different format, and we'll let Wolfram Alpha solve it, and there's quite a lot of calculations, but finally it will come up with this answer, which is 63.1%. Amazing. We got our confirmation. After we've done all that, I want to take a step back and acknowledge that no real person would employ a Nash equilibrium strategy in real life. Everyone would act according to their social preferences and maybe global cultural zeitgeist. And that's what I'm going to focus on in my next video. Please subscribe if you find it interesting and don't want to miss it. See you next time.